Hello students, this is lecture number 13. Okay. So far we have looked at the stress analysis problem from different perspectives. So we had the strong form, okay, we had 1D, so this is for 1D elasticity problem, or stress analysis basically. So we looked at the strong form, then we looked at the weak form, then minimum potential energy formulation. Okay. So this was important, weak form was important for Galerkin method. Minimum potential energy formulation was required for the Rees method. Then we looked at the different point of view, the weak form as the virtual work, yeah, and the minimum potential energy as a functional, yeah, of the variational calculus. So these are different point of view, and you will see like this course is taught from different perspective as well. So it's possible that somebody who is teaching you finite element can start with variational calculus, and from this point of view he will teach the whole class. It's possible. So more mathematical basically, yeah, or maybe some teacher may not even mention this variational calculus, so you can just start from the strong form, go to weak form and just use the Galerkin method, yeah. Or if it is a structural analysis, for example in case of civil engineering problems, this is mostly a structural analysis problem only. So in that case you just start from the minimum potential energy formulation, but basically all are related. That's what I have seen. Even like minimum potential energy formulation itself comes from the Castigliano theorem. So this is you can see that Castigliano's theorem, right. So Castigliano theorem says if psi is the potential is the strain energy, then it says F equal to psi over, so F I is equal to Ui. So basically what it says that if psi is a function of different forces, so different displacements at those corresponding to those general forces, then you can find out the force by partially differentiating the strain energy with respect to the displacement corresponding to that force. Or similarly you also write Ui is equal to del phi over del phi, yeah. So basically this is the next the minimum potential energy formulation. This is based on actually what the Castigliano theorem does, right. So you can see the similarities in this way also, like say what do you say, just to give you idea, not exactly that, but just to give you idea, what I am saying is f equal to del psi over del u in general, right, or del psi is equal to f del u, yeah, okay. So that tells you that del psi minus f del u equal to 0, or psi minus f u equal to constant, right. So that tells you that at this is the state energy minus this is the work done equal to a constant. So basically a minimum value, right, so a minimum value where if it is in equilibrium, right. So this is nothing but what is this? Potential energy only. So this is potential energy. So this equal to potential energy equal to a minimum a constant, means actually this really means that this is a stationary point basically. So this is 0 means a constant, means the value will not change. This is the a minimum point, right. So a minimum value. Okay, so see here there is here I just want to relate, so no, I did not want to derive it or anything. You will see like f could be f may also be varying, but in this case you are assuming that f is constant, a force f is applied, so f is constant over the whole time, so but in real life if you apply slowly, but here in this case you are applying f fast, that's the difference. But in any case, like this is how these are related. So from where this is the potential energy terms comes equal to state energy minus work done. So at least this will relate to the Castigliano theorem. So this is based on the Castigliano theorem. So I will just write it. So this generally you study in the solid mechanics, yeah, in mechanical engineering. Okay. Okay, even if you did not understand, you never had Castigliano theorem in your course, but don't worry, okay. So it is just extra additional information I gave so that you can so that mechanical engineering students can relate to the solid mechanics. Otherwise, there is no much use, okay. Okay, now we have spent so much time on elasticity problem, 1D elasticity problem, but here the finite element course is not just for the elasticity problem. We can also have in heat transfer problem, for example. I will give some example. So heat transfer as well, right? And here the problem could be as we had 1D problem. So maybe like this, we have x equal to 0 here, x equal to L, and then there could be a temperature defined. So T here, T x equal to 0 equal to, let us say, a given T naught is given, right. and then and at the other end there may be q given, right. So, q at x equal to L may be given as, let us say, is called q naught, which is given, right. Okay. Now, we have to relate, and we have to actually find out the equation, governing equation in this case. So, let us take one slice. Okay. So, we cut a slice such that this is dx. Okay. Area we can assume and everything. So, if you draw the slice here, which will look like this one, and what we will see, we want to see what is the energy coming here. So, say this is the energy q which is coming, q, okay, and at this end we have q plus dq over, so not partial, actually it will be total differentiation dq over dx times dx. Okay, fine. So, here q is again this we have to write in terms of, if q is per unit volume, per unit area, per unit time. So, q we have to define, right. So, thus q will be is the heat flux, yeah, okay, heat flux. So, since area is important, so the way we wrote in case of a stationary analysis, q times A. So, similarly here we have to write q times A, because area could be varying. So, we have to write q times A. So, write q A. So, here also let us write q A plus, yeah. Okay. So, we have q A here, then q A plus dq A divided by dx dx. Okay. So, this is the q is heat flux, and that means the heat coming to the system per unit area per unit time. Okay. So, this will be like watt per meter square, we will have SI unit, right. Okay. So, and there could be some heat generation terms. So, let us write S, yeah. S is the body heat generation, and this will be watts per unit meter, right. So, here it is distributed. So, per unit length, so S is per unit length, and again, but it is being supplied per unit time. So, this will be watt per meter, yeah. So, the heat generated per unit time per unit length, yeah. So, if you take from here to here, then for the whole heat, if you want to find out, so then you have to multiply with S times dx, will give you the total heat generated per unit time inside this control volume. So, we write S here. Okay. Now, total heat we have to see that has to be conserved, right. So, heat total heat coming to the control volume. So, this is a control volume. Okay. So, the length is dx, area is A. So, what do we get? We get one thing here, we have to change the direction of this. So, this okay. So, this arrow will not be like that. So, this will be go outside like this. Why? This is because if you Q depends on what is Q? Q depends on the what is the temperature here and what is the temperature here, right? And Q is defined as, if you, so how do you Q will be equal to minus K dt over dx. This is how you define, right? So, where K is thermal conductivity, yeah. So, for this control volume, let us say this T1 is greater than T1. So, that means heat will flow T1 to T2 because T1 is bigger, and heat will flow, the direction will be like this one, this will be value of direction of Q, and the Q will be the same direction here also, because Q at this phase is given by T1 minus T2. Here also will be given by T1 minus T2 only. So, direction will be positive this way. Okay. So, Q, that means you have to be consistent, hence we cannot have here coming like this one and here also coming like this one, you know. So, since we are defining the Q, and Q will depend on this T1 and T2, and for both of them T1 T2 is the same. So, that means if here the heat is entering, this must leave at the other end, and hence we have to write like this. Okay. So, now we have to find out the heat coming to the control volume, and this will be equal to simply this is coming, this is going, and S times dx is also coming, right. So, because this is the internal heat generation, yeah, and hence what we get? We get okay. So, this I will write next page. Okay. So, total heat coming to the control volume is equal to, we have this one which is going, then this is coming, and then S times dx will be also coming, right. So, coming will be this plus this, and then this is outgoing. So, accordingly we write. So, we will have Q times A plus S, right. So, Q times A is there, then plus S times dx, then we have minus QA plus dQA by dx times dx, yeah. And total heat coming to the control volume should be 0, because since energy conserved, so conservation of energy, and or what we get? We get, if we say this is cancelled by this one, and then we have simply this and this, yeah. So, we have or minus dQA over dx, yeah, plus S equal to 0. Okay. We can expand further. We further know q equal to minus k dt over dx. Yeah. Okay. So, this is also known as Fourier law, and this is basically we are going to put that in here. This is the heat flux is in terms of temperature, and we are going to put it here, and what do we get? We get minus d over dx times a, and then we have q, which is given by minus k dt over dx, right, okay, plus s equal to 0, or if you simplify you will get d over dx, then we have k a, then d t over dx plus s equal to 0. So, this is what the heat conduction problem. Yeah. Plus we have to write some boundary conditions. Boundary conditions. So, boundary conditions could be like in the problem here we are writing t at x equal to 0 t 0 and q at x equal to L is q naught. So, this you are defining. So, this we can write basically this in terms of the boundary conditions. Boundary condition could be anything as per the problem, but in this problem since we have like this kind of t 0 equal to t naught and q at L equal to q naught, then we can write accordingly boundary conditions according to this will be t 0 equal to t naught, and q in this case is nothing but minus k dt over dx at x equal to L, yeah, will be equal to q naught. So, you can write like that. There could be any other kind of boundary condition as well. So, examples of other boundary conditions. So, there could be convective heat transfer. So, in which case let us say at the end at this end you may have, so next page. So, let us say example 2 we may have at the other end. So, let us say we have t 0 equal to t naught, and here we have t infinity here, yeah, and this is L, and H is given. So, H is convective heat transfer coefficient, convective heat transfer coefficient. So, what is the meaning of that? This meaning of that is Q. Q means the heat which is this will be typically at the higher temperature. T infinity is the ambient, it is called ambient temperature. So, if temperature here let us say is higher than this one, then there will be a heat transfer, there will be a cube which will be going outside like this. Yeah, so then the heat which will be losing this one, yeah, so the Q will be Q equal to H, and then you have T where L minus T infinity, right. So, this is automatically, this applies the basically Q at L. So, we have to write Q at L. So, this will be Q at L equal to, this is what it tells you. So, Q at L will be equal to, what is the temperature here at this end, minus what is the temperature, ambient temperature, and then multiplied by H. This is another boundary condition you have to apply, right. So, this is another boundary condition. Remember in this case that you have a T here. So, accordingly you have to, when you apply, accordingly you have to take care of that. Okay. So, this Q is a function of T itself, what is the temperature is here. So, this is another kind of boundary condition that can be applied here, or in some cases even can be applied at these boundaries as well. So, you have to be careful accordingly. Okay. So, here we can write, since Q is, we know, is minus K dt over dx at x equal to L will be equal to H T at L minus T infinity. So, we can write like this one. So, this is what is known as convective boundary condition. Yeah. So, convection boundary condition. Yeah. It may be possible that the boundary conditions are also given in terms of Q bar. Okay. So, what is the meaning of Q bar? It is possible that say example 3. So, it is possible that the value is given as, say you have T naught here. So, this is L. So, you have T at L equal to T naught, yeah, and given Q bar at x equal to 0 equal to Q bar naught, let us say it is given like this. Okay. So, here the meaning of this is basically Q bar where Q bar equal to Q dot n, where n is equal to a unit vector perpendicular to the cross sectional area, to the boundary cross sectional area. So, what is the meaning of that is, here if the area is like this one and n will be here and here n will be here, so this is outward. Okay. So, area that n is projected outward. So, what the meaning is, we have n here this way and here you will have n this way. So, basically this indicates the area vector divided by total area. Yeah. So, this is simply, you can also write equal to area vector divided by area. Yeah. Okay. So, Q dot n will tell how much the flux is along like outside, pointing to the outside of the domain. So, it indicates the heat loss basically. Yeah. So, basically it tells you the heat loss. So, this is telling you if q bar is given. So, q bar at this is this one, that really means the flux is this much and this is going outside of the domain. So, the value is this and this is the loss, basically that is what it tells you. Yeah. So, in this case, if let us say it said that q bar 0 equal to, let us say 5, it is like this. That really means that means you have to write minus k dt over dx, yeah, and then this is what the q is here, right, this is what the q is here, dot n, and n is value is minus 1, right, this is going backward direction. So, hence we multiplied by minus 1, right. Of course, this is at x equal to 0 and this is equal to 5. So, or it tells you that k dt over dx at x equal to 0 equal to 5. Yeah. So, this is how you have to interpret. Similarly, we can have diffusion problem. Diffusion. Okay. So, the problem actually this is exactly like a heat transfer problem only. So, let us say you have one dimensional medium and some species, some ions or something is flowing, right. Okay. And there is a fixed law and which says that again this is a q equal to minus d and you have dc over dx. This is the fixed first law. Yeah. So, this is the fixed law and where d is diffusivity, yeah, and c is concentration, okay, and q is flux, again defined in terms of flux is number of ions basically based on that. So, this is will be moles per unit area per unit time. Yeah. So, this is what the flux is. Okay. So, here also we can do the similar formulation. So, we will have a control volume, a small one, this one is x equal to 0, this is x equal to L. You have control volume. So, you have like this and you can do the similar thing. So, there is a q times A gives you the total number of species entering the control volume and then there will be something which will be leaving and this will be d over dx qa plus qa itself. Okay. Then there will be some generation term also, some species being generated, let us say this called S, and then we do the total charge or total number of species or conservation of mass basically. Yeah, so has to be convert the conservation of mass you have to apply here, and what we will get simply is, you can say mass is conserved, and hence you will get this this plus this, right. So this is a q times a will be for the whole area. So we can write that here. So we get qa plus s times dx. So this is dx, okay, then minus d over dx, qa minus qa is equal to 0, or simply you will get minus d over dx multiplied by of qa plus s. So there will be dx term also here, minus like this. So there will be dx term here. Okay, so let's multiply, pre-multiplying this here, dx. So dx multiplied by dx over qx plus qa. So plus s equal to 0. Okay. So if you see that this term is actually similar to what you got in case of the heat transfer basically, right. Next is, we also know that q equal to this from the Fick's law, so we can put that value here, yeah, and we will get, since q equal to minus d dc over dx, your equation becomes, we will put to this one. So minus d over dx, then area will be there, and then q terms minus d dc over dx plus s equal to 0, or d over dx, and we have d times area dc over dx plus s equal to 0. Yeah. So this is what the equation is. Again, this is similar to the heat transfer problem, only thing, instead of c you had t there, instead of d you had k there, otherwise everything is the same. Okay, so boundary condition also can be similar to the heat transfer problem, but there is no convection in this case. So we can have sorry, not t, x equal to 0, x equal to L, you can have c at x equal to 0 equal to c naught, and you can have something, this example, and you can have q at x equal to L is equal to q naught, some value q naught possible. Yeah. Okay, there is no convection, this is the convection heat transfer type of thing here, but there is something called advection, right. So there may be some advection. Okay, so advection is because of the flow. So it is possible that you also have some u, there is some u velocity of the fluid as well, it's coming, right. So let's say if you had u term as well, u, okay, advection means you have velocity of the fluid, of the fluid is also there. Yeah. So, in that case we have to add the advection term, and in that case the we will have a different little bit different a strong form. So, let us see if you add advection then what happens. So, with advections, yeah, here you say diffusion with advection. Okay. So, now problem remains the same like this one, but only thing is it also have a u term. Let us say this is u, the velocity of fluid, velocity of the medium, we can say of the medium. Okay. So, we already had a control volume, similar kind of thing we can also have right now, but we have q here, q times a, then we have qa plus d qa over dx times dx. We had s term. Also there is a velocity, right. So, u, with u it is going, and here this is coming out. So, if you see there is a net, there will be a charge going, or the species going with the velocity because of the concentration, because there is a concentration, this is going like this one. So, here because of the velocity we will have c times u, right. So, this gives you basically the c is the concentration, and u is the velocity. The concentration is typically in moles per volume, and u is meter per second. So, what you get is this will be moles, c times u will be moles per area per unit time, but you have to multiply it by A as well, so that you get the total, yeah, total material going to the control volume per unit time. For that you have to multiply it by A. So, we have like that. Yeah. Similarly, here this will be the one, because of the u there will be assume u is constant, right. So, here you will have u times, and there will be variation, there could be variation. So, we will have q c a and plus d c a over d x times dx. Yeah. So, since medium is also flowing, so this much species are entering the control volume, and then this is also leaving it, because why? Because maybe concentration is changing here, because why? Because a species are also generated, because of the body source is also there. Because of that, also the pipe itself maybe the cross sectional area is decreasing or increasing. So, this also you have to take into account. So, basically this is a q times, this equivalent to q times a, right. So, then we can now see what happens. Yeah. Okay. So, now again the mass is conserved, and hence we will have what? We will have qa plus cua plus s times dx, then we will have minus qa minus dqa divided by dx times dx, then we will have minus u Ca plus d Ca over dx, okay. Total has to be equal to 0, right, okay. And you can see here this Qa will be cancelled by this one, this Cu will be cancelled by this one, okay. So what we will have, simply this cancel, and this cancel, we have this term and this term and this term multiplied by this one. So we will have S minus d Qa over dx. So let's we will write here itself final term, the final terms what looks like. Let's use a different color, probably let's use blue. And what do we get? We get d minus d Qa divided by dx. So we are leaving dx in all of them, okay, done. Then we have this term, okay. So we write minus u d Ca over dx, okay, done. And then we have S term, so plus S equal to 0, okay. So this is what our equation is, yeah, okay. We can add there the value of Q that we know from the Fick's law. So we can write that since Q equal to minus d C over dx, okay, then our equation becomes we had minus first, so minus dq dA, like that term will be there. So we write minus d over dx, then a, then minus d dc over dx, term is there, okay. Then plus, sorry, minus again, minus d over dx, sorry, let's go back, see, minus u times this, yeah, okay. So minus u, we can simply write minus u times d Ca over dx. We can write as straight away, nothing will change. So u dc over dx plus s, okay. So here plus s equal to 0, or we can rearrange, say d over dx, we have dA dc over dx plus s minus u dCA over dx equal to 0, okay. So this is what the final equation is, diffusion with advection. So you have the advection term here, this is advection term, yeah, okay. This one you know, this is the body source, yeah, and this one coming from the Fick's law. Okay. So this is what the diffusion is, diffusion equation looks like, and you may try to these are the strong form, right. So, this is the a strong form, and you may try to convert this into the weak form. So, if you want to solve diffusion problem or the heat problem, so whatever a strong form or the differential equations we derived in this video, you have to convert them into the weak form, okay, before you can solve it, if you want to solve it using the Galerkin method. We are now done with chapter 3 now. However, I will just add few things to make it little bit more rigorous. What I mean to say is, as I said in the beginning itself, I am going to like focus on mechanical engineering problems only. That too, I said that you will be using more of physics or mechanics rather than mathematics. So, hence I will not be mathematically rigorous, but at the same time there should be something that I think I should mention, otherwise there may be some questions which you will not able to understand in your textbook only. So, we want to know what kind of function our test function or weight function can be. So, test function, in order to solve the differential equations we have studied, once you converted that into weak form, then you have a test function, whether this is ux or tx or cx depending on the problem. So, ux in stress analysis, tx in heat transfer, and cx which is the concentration in the diffusion problem, and similarly other kind of problems that you can derive, or you ready made, you have the differential equation ready made, and then from there also you can do. And there is corresponding weight function, right. So, we have weight function, and we called it wx. So, we know that we can take any kind of function, but what kind of function we can take. Okay. So, there are few jargons that I want to discuss, so that you know, if somebody who knows the finite element methods and he is talking to you, then there may be some jargon. If he talks to you, you should be able to understand. So, what we say here is ux and wx have to be admissible. Okay. So, the jargon is the admissible, and sometimes also called kinematically admissible. Kinematically admissible. Okay. So, remember this, the kinematics means actually the displacement, right. So, we are only talking about the displacement, but not about the forces. There is a force and displacement, there are two things, right. So, as you know, the whole mechanics has two parts. You call it as statics, and then you have dynamics, and dynamics also had two parts. One is called kinematics, and the other you call it kinetics. Yeah. So, kinematics is more like displacement, only, or kinetics is about the forces. Okay. So, basically when you say kinematically admissible, meaning that if ux is kinematically admissible, then ux satisfies the essential bounding condition. essential boundary condition. So, this test function, any test function ux is said to be kinematically admissible. That really means ux will satisfy the essential boundary condition. So, at the boundary if u0 equal to u0, that test function should satisfy. Okay. Similarly, when you say weight function is kinematically admissible, right. So, when say weight function wx is kinematically admissible if wx equal to 0 where ux is pre-specified. Where that is at x where essential boundary condition is given. Right. So, that means this takes care of those essential boundary condition. If wx equal to 0 where ux is defined or is prescribed, then we call it the weight function wx is kinematically admissible. So, this is just the term, okay, just to talk to somebody very easily, basically to communicate for better communication. But you understand, we have already talked about this, that wx equal to 0 where ux is given, right. So, we know that. Apart from that, this is also the smoothness requirement of like what kind of function that ux and wx, what kind of function. Functions. Yeah, we have seen that the meaning of wx is basically it is same as, it has the same unit as ux. So, the nature of wx is the same as ux only, right. So, we have seen that, we have seen from the virtual work. So, w is nothing but this is also virtual displacement only, right. So, basically both have the similar meaning basically. So, whatever condition applies to one also applies to the other, as simple as that. Okay. But in general, if you want to talk about what kind of function it can be, like in terms of a smoothness. So, there is something called a smoothness. Okay. So, simply there will be Cn smoothness, yeah, Cn smoothness, or you can say C minus 1, C0, this kind of. Okay. So, what is the meaning of that? Okay. So, basically if this Cn, when you call, this is a set of function which has n continuous derivative. So, if let us write like this one. Okay. So, if ux is a member of Cn, okay, where Cn is a set. Okay. So, this means, so then ux has n number of continuous derivative. Okay. So, that for example, see, let us say this. You have a ux equal to say alpha plus beta x, if you have like that. Okay. So, you know that you can differentiate it once, right. So, this is going like this, this is going like this one. So, this can be differentiated, yeah, but if it is a smooth, like it is, you can take du over dx, it will be beta, you know. So, but we have to see the within what domain you are talking about. Okay. So, from just saying this one may not be that clear, because there could be a combination of lines and all. So, for example, let us say you are going like this. So, your domain is from here to here, and your line, you are going like this. Let us see like this. Okay. So, x equal to 0 there, L equal to x equal to L, and then let us say this is what ux is. So, going from here, then suddenly goes up. Okay. So, goes up and then suddenly goes up. What we see here, this is not, function is not differentiable here, right. So, it is not at all the differentiable, right. So, this one is you call it, it cannot be differentiated, and then the here the smoothness, actually this is not a smooth, right. So, this is what it tells you, is basically this is not a smooth, forget about the derivative being a smooth. So, you will call it, this is example of C minus 1, right. So, now in this case ux will belong to C minus 1, yeah. So, this is C minus 1 is smooth, right. Okay. Now, second example we can take where we are varying x, and you have ux, and could be wx also, and you have like goes like this. So, you have from here to here like this, then goes like this one, and goes like this, right. And this is how this is till L, 0 to L. Now, what you see is this is a continuous function for sure, but is the derivative continuous? No. If you take the derivative, this will be here, this will be here, then this will be here, right. So, value is a small value, this is a high value, a small value again. So, derivative, if you see du over dx, and if you plot it, this will be something like going from 0, then you have here, right, and then you will have like this one. So, du over dx is not continuous, okay, not continuous, right. So, this is C, so this is not continuous. Okay. So, this is called C0, this is example of C0, okay, this is C0. Okay. Now, second, the third example, we can give x, and in this case you have varying, this goes like say if you integrate this one, okay, you are integrating this, yeah. So, then what happens? So, this will be quadratic, yeah. So, this will go something like this, yeah, and will go like this, and then go like this one, yeah. So, you have integrated this and got this one. So, let me write. So, you have integrated this one to, and then you will give this a smooth, right. Okay. Now, you know that if you differentiate this, so this is ux. So, if you differentiate this one, then you get a smooth, this not a smooth, but this is the continuous curve you will get. Yeah. So how many continuous derivative can you get? You can get one, right? So hence you will call it C1, right? This is C1 smooth, right? And so on. If you integrate these two, then you will get even C2 smoothness, right? Okay. So let us say write that also. So let us say integrate, okay, and then we get even more. So let us say you are going like getting like this one, yeah. So in that case this will be C2 smooth, because it will have two continuous derivatives. The first derivative will be this one, derivative of this will be also continuous. So you will have one this, second one this one. For this only this you get. For this you have no derivative which is continuous, because you get discontinuous derivative, hence it is C0. Okay. So this tells you how many derivatives which are continuous. Okay. So this is what this is. Okay. The next thing could be what is known as H. You write it as H1 like this one. Yeah. So this tells you basically, if let us say Ux, okay, so let me write nicely. So if if U is a member of H, let's call M, okay, then Ux has M derivative which are square integrable. Okay. Okay. What is the meaning of a square integrable? Okay. So a square integrable. Okay. So a square integrable means say fx is a square integrable if we are integrating fx over some domain. Okay, so integrable in a given domain. Okay, this understood. A square integrable, so we have to square it, yeah, and then we have to integrate over the domain, and has to be less than infinity, right? So this is the means the value should not be infinite. That really means this term should be finite within the domain, right? That is what the meaning of that. Okay, so this that really means, roughly means, if the square of fx should not be infinity, yeah, within this domain. So in the domain means, in this case, since we are studying 1D problem right now, so that really means from x equal to 0 to x equal to L, the fx should not be infinite, right? So for example, tan x, for example, right? So if x is in degrees, then you know that at 90 degrees this will be infinite. So this should not occur. That really means. Okay, now, so a square integrable. What is the if Ux belongs to is h to power m, then ux has m derivatives which are square integrable. Okay. So, now derivative, that this tells that the derivative has to be finite. That's it. And example we can see, if let us say, if when you say h1, h1 meaning that if u, so if ux belongs to h1, that then ux has one derivative which is square integrable. So, what is the example? Example could be, say, let us say this example. So, you have x here, you have ux here, and let us say similar example that we had this kind of, right. So, we have L here, this is 0. So, what do you know from here? That this denotes that we will have du over dx, right. So, we have du over dx means derivative, and since all the three are lines, different slopes, so we assume this will be here, and then we will have here, and then we will have here, something like that, right. Okay. So, now what you see, there is a jump, sudden jump here, jump here. Okay. So, this has, if we differentiate further, what will you find it at this point? It will be infinite, right. So, du over dx will be infinite, we can say, or maybe just not defined itself, right. So, this will be something like this. So, further, if d square u over dx square will have at this point, this is the differentiation, if you take this will be sort of infinite, right, or maybe it is not defined itself. So, ux will belong to what? We can integrate, right. So, we can write I equal to du over dx, right. So, du over dx square, and we can integrate over the whole domain L, right, and it is possible, right. We have du over dx, so this is finite from here to here, here to here also is finite, here to here also is finite. That really means we can actually, derivative of u is a square integrable. So, we know that this will be less than infinity for sure, because u is linear. So, du over dx is, we have the constant like flat curves here, and hence if you integrate, this will be the area, this will tell just the what is the area under this curve, which is finite, right. So, and hence this is less than infinity. So, that really means this tells you that ux is h1. So, ux belongs to set h1, right. So, this is example of h1, right. Similarly, the example of, if you say h2, then similar to we can take basically this is what you are seeing is it belongs to h1 and also belongs to c, this is also c0, right. Okay. So, if you integrate this, okay, so let us integrate this one, integrate, okay, and then we will get something like this. So, we have the curve which will go like this, let us say, yeah, okay. So, if the curve is like this one, then this curve, so let me write, this is ux, this is x, and this curve then will be C1. We know that it has one derivative which is continuous, which will be, take the derivative of this, which will be this one, right, okay, and also it has two derivative which are square integrable. So this also H2 belongs to H2. How? If you take derivative of that, you get this one. So hence you can integrate it, which will be the area under this curve, hence which is finite. This is the first derivative. Then derivative of this itself is a square integrate. Okay, this is a square, sorry. So it is not just area under the curve. Basically this is a square term here. It's not just without a square. Okay, so what I said about this, just the area, is wrong. It has to be a square of that. Okay, so we have to square it. Yeah, so du over dx a square you have to do, then we can find out what that curve is. Then the area under that curve will be the one value of I. Anyway, but convey, the meaning is conveyed basically. So if we take first derivative, we get this one. A square of this also will be something like this, and which is again take the integrate it, we will find a finite value. Now next thing, we differentiate this, which becomes like this one. Now we take the square it, so we get this kind of profile, and then we integrate it, that will also be finite. So hence we are getting two derivative. One derivative is this, and derivative of derivative is also square integrable, and hence there are two derivatives, hence H2 term is coming, and we have C1 because this is C1 because it has only one derivative which is continuous. Okay, you differentiate this one, you get discontinuous, hence you have only one. So this is the term that you should understand. This is well, for mathematics students this may be already known, but for engineering students this will be something new. And also when you are solving the exercise problems, these terms may pop up, so now I hope this is going to help. So okay, so with that we have finished chapter 3. Okay, so we will start with chapter 4 in the next lecture video.